What if your idea of a dinosaur looked like a duck, a bat, and a crocodile on the same menu? Welcome to the weird side of evolution. Today, we're touring 4 body plans that feel impossible until the fossils force us to take them seriously.
These aren't movie monsters. They're real solutions to survival problems. But to understand them, we need a tool.
We call it the Weirdness Lens. 3 checks for every fossil. First, shape.
Do we see a sail? A membrane wing? Arms that are absurdly long?
Second, habitat. Where did it move? River edges, open water, forest canopy?
And third, toolkit. What does the body make easy? Eating, moving, displaying, defending?
By the end of this episode, you'll hear how paleontologists turn bone clues into the most cautious version of behavior.
And we'll flag exactly where the evidence ends and where interpretation begins.
On the map, the Kem river systems of Morocco, the Namek wetlands of Mongolia, and the Jurassic forests of northern China. Let's open the first case file. It involves a tale that changed an entire argument.
Paleontology isn't guesswork. It's inference from evidence. Think of it like a ladder.
Bones give us the frame. But how do we get the weird details? Skin, feathers, wings.
Rung 2. Soft tissue impressions. Rare, but when they happen, rock can preserve outlines of skin, feathers, or membranes.
Okay, shape. What about diet? What did it actually eat?
Sometimes we get direct contents, gastroliths, stomach stones, or even fragments of a last meal inside the rib cage. For movement, we look at trace fossils. Footprints are behavior frozen in stone. But remember, a trackway is a snapshot, not a movie.
And what about the stuff you can't see? Inside a skull, or how a tail moves in water?
Top rung, CT scanning and 3D modeling. We can look inside a brain case or test how a tail might perform without damaging the fossil. That's why we'll use a confidence meter throughout.
So how do we score it?
Bones plus direct impressions. High. Strong anatomy with good comparisons. Medium. Mostly models and assumptions. Low. Now, Spinosaurus. In 2020, a paper in Nature described a much more complete tail from Morocco's Kem beds. And it didn't look like the stiff, balancing tails we see in most large theropods.
On screen, you can see the punchline. A tail shaped more like a paddle, tall, vertical, and built to push water.
Exactly. The tail vertebrae have unusually tall spines and deep chevrons, creating a big, fin-like surface. The researchers tested physical tail models in a water flume, and that tail shape produced more thrust and efficiency than typical terrestrial dinosaur tail shapes.
So, Weirdness Lens. Shape, a fin. Habitat, water-associated.
The anatomy strongly suggests strong swimming performance. But we have to be careful about the next step.
What does a paddle tail not prove?
It doesn't prove Spinosaurus was a deep-diving, high-speed pursuit predator. A finned tail can help with propulsion, but also with stability, turning, and holding position in current. The tail tells us what it could do, not exactly how it hunted every day.
We have the engine. We don't have the full driving manual.
Right, and that's why Spinosaurus stays debated. Most agree it was closely tied to waterways and ate lots of aquatic prey. But researchers still argue about just how submerged it was, and whether it hunted by active pursuit, shoreline waiting, or ambush. For nearly 50 years, this dinosaur was a ghost. In 1965, in the Gobi Desert, paleontologists found gigantic forelimbs, about 2.4 meters long, and almost nothing else.
On screen, that scale hits. Those arms are longer than most adults are tall. No wonder people imagined a nightmare predator attached to them.
But in 2014, 2 new skeletons described in Nature finally filled in the blanks. And the full animal wasn't the super predator people pictured.
It's huge. It has tall back spines that make a hump, and the head, wide and toothless, gives a duckbill vibe.
Superficially, yes. A broad, toothless snout built for a similar job. That's convergent evolution. Similar tool, different family tree.
So, giant arms, a hump, a broad bill. What was it doing with that toolkit?
Here's the rare part: direct diet evidence. The 2014 study reported more than 1,000 gastroliths, plus fish remains in the body cavity. Strong clues that Deinocheirus was a mega omnivore in wet, mesic environments.
So, not a slasher, more like a gigantic, adaptable forager.
That's the safe read. Plants, animals, and a lot of time around waterlogged floodplains.
If you saw those arms in a movie, you'd assume predator. But the weirdness lens keeps yelling, tool shapes can lie.
Exactly, and nowhere is that clearer than our next oddity, Therizinosaurus.
Hold on, how do we get plant eater from Edward Scissorhands?
We lean on relatives. Therizinosaurus itself is famously fragmentary, but close therizinosaurs, like Erlikosaurus, preserve skulls with beaks and leaf-shaped teeth, traits that fit herbivory better than meat slicing. Evolution repurposed a theropod body plan. Less emphasis on cutting bites, more on processing lots of plant material.
Okay, but the claws, if they aren't for hunting, what are they for?
This is where we use multiple working hypotheses. One idea is hook and pull, using long claws to drag branches closer. Another idea is display. A 2023 biomechanics study argued that the biggest therizinosaur claws, including Therizinosaurus, were long and relatively slender, likely too weak to take heavy combat loads, making showy signaling a plausible explanation. So, same weird tool, multiple plausible jobs. Now meet Yiqi. Described in 2015, this small dinosaur from Jurassic rocks in northern China surprised everyone.
On screen, look at the wrist. There's a long, extra rod-like bone. What is that thing doing?
That rod is the key. The fossil preserves patches of membrane associated with the rod and the fingers. It suggests an aerodynamic surface made partly of skin membrane, not just feathers.
So it flew like a bat?
Not exactly. It's convergent evolution. Similar idea, different construction. The membrane evidence is strong, but powered flight like a modern bat isn't something the fossil alone can prove. Models tend to favor gliding, or at least very limited flapping compared to true flyers. It's an evolutionary experiment near the broader origin of bird flight, but the exact performance lives in model-based territory.
Nature trying options.
Exactly. We have the membrane. The flight mode is the part we have to score lower on certainty.
So what does exotic really mean? Not imaginary, and not a movie monster.
It means a lineage tried a body plan we don't expect, and left enough evidence for us to test ideas carefully.
Let's run the weirdness lens one last time. First, Spinosaurus in Morocco.
Tail anatomy strongly supports serious swimming capability. The debate is the lifestyle details, how often it submerged, and whether it hunted by pursuit, wading, ambush, or some mix.
Next, Deinocheirus in Mongolia. It went from mystery arms to a humpbacked, broad-billed giant.
Direct stomach evidence supports an omnivorous diet that included fish. And the rest, daily behavior, stays inference.
Then Therizinosaurus, also in Mongolia. Proof that giant claws don't automatically mean predator.
Those claws may have helped with foraging, signaling, or defense. We have the tools, but not the user manual.
And finally, Yiqi in China, a dinosaur with a membrane wing.
The fossil supports a membrane-supported wing surface. Modeling suggests gliding is plausible, but the exact flight style remains debated.
Dinosaurs weren't one look. They were a library of solutions. Which clue should we decode next? Comment below. Tail, tooth, claw, or track? I'm your host, and I'll see you in the next era.